Hi, in the last session, we talked about VHDL packages and libraries. We discussed how to create your own custom package and how to use them in your VHDL designs. Now, let's talk about parameterized components. Parameterized component is a crucial topic that enhances the flexibility of your VHDL component. By understanding this parameterization, you can create more versatile and reusable designs, which is essential in complex systems where different configurations are needed. And that is possible without altering the core logic. So let's start. VSDL includes a feature called generics, and that helps to parameterize your modules and components. Generics are treated like a special type of constant that can be customized for each instance of your module so that your designs become more adaptable to the VHDL requirements. So the basic requirement for a generic is similar to a constant, means it must have an identifier. It must have a data type such as integer, std logic, or boolean, etc. And with all these abilities, generics in VHDL can be used in various scenarios, such as setting vector sizes or enabling a specific feature within your module, etc. Now, because we have taken a reference of constant to understand this generic concept in VHDL, so it is important to understand how generics are different from constant and how to use both of them individually in your designs. First, quickly see about constant. So constant are declared in the declarative part of architecture. So your constant can be consistently used within the architecture module in your design. And because it is a constant, so it has the same or fixed value across all the instances of your module. That's one thing. We can also declare constant within a package as well. This is helpful when you're required to access that constant across multiple modules. This approach is recommended because it provides the constant with global scope and that make it accessible through the entire design and ensure the consistency in your designs. Once you declare a constant in a package, its value remains the same across all the components and subcomponents within that design. So that maintains the consistency and reduces the chances of errors because of mismatch in values, etc. Now let's talk about generic. So generics in VHDL are identified in the entity declaration, and its scope is limited to a single instance of a VHDL component. This means that each instance have its own unique configuration. So it enhances the flexibility of your design. The main difference between a generic and a constant is that the generic scope is limited to a single instance of a component. However, a constant value remains the same across all the instances of that component. So, generics in VHDL allows you to do the unique customization for each of your instance. So, this is the advantage of generic that their values can be unique for each instance of a component. So, the benefit is that you can use the same component with different configuration and sizes without changing the configuration on your original component. And this feature is really powerful if you know how to use it because it allows you to assign different values to the generic parameters for your multiple instances of the same component. This flexibility is particularly useful for large designs where different configurations are needed for different parts of your system. So let's understand this with an example, and it will help you to understand how generics can be used effectively. So this is our example. In this VHDL designs, we will perform a simple addition operation. So our adder module has two input ports, input A and input B, and one single output port, D out. The adder module adds the value of input A and input B and assign the output to the D out. So this is simply a basic arithmetic operation. So here is the VHDL code for this. Entity half adder is port A colon in std logic vector 7 down to 0. B in std logic vector 7 down to 0. D out std logic vector 7 down to 0 bracket closed and entity semicolon. Architecture. My design of half adder is Begin. D out gets a value of A plus B semicolon and architecture semicolon. This is a simple program. But the problem with this code is, or you can say the limitation with this module is that it can only handle 8-bit numbers. Means it can be only used to sum 8-bit two inputs. But what if you want to add two 4-bit inputs or 16-bit inputs? That is not possible with this program, right? So this code has limited usability, means it cannot be used for different vector size operations. It is just for adding two 8-bit inputs. So you cannot use this component for the addition of 12-bit, 16-bit or even 4-bit numbers. So in the next slide, we will see that how you can use generics in VHDL to make this code more versatile and usable, so that the same module can be used for adding the operation on different vector size inputs like 4-bit, 8-bit, 16-bit, etc. we are talking about. Okay, so let's see how we can achieve this through generics in VHDL. First, we will declare our generic for the VHDL code. Generics are declared in this section here, that is above the port declaration and within the entity declaration. So our VHDL code looks like this. Entity half header is generic, then in the bracket x colon integer colon equals to 8 bracket closed semicolon, port a colon in std logic vector 7 down to 0, b in std logic vector 7 down to 0, d out std logic vector 7 down to 0 bracket closed semicolon and entity semicolon. So you can see that this code is identical to the previous VHDL code, except the few additional lines between the entity and the port section. So we declared generic X before the port declaration in this entity section. So let's see how we declare generics in VHDL. We declare generics using the generic keyword. Then inside the bracket, we list all the generic values and setting up the parameters for our modules. You can also declare more generics here if needed in your design. In this example, we just need one generic value, which is x, and it is integer data type. And this value will control the vector size of our code, or you can say the vector size of inputs and outputs. We can assign a default value to generics as well, and this is optional. For example, we have assigned 8 in this example here. This means if you do not specify the value of x while using it as a component, then it will default consider it as 8. Next, we will see how to use this generic to define the width of your input and output ports so that you can control your bit sizes dynamically. It is quite simple. Just define all the ports with the range x-1 down to 0. Means we use the generic value x to set the width of our std logic vector signal. Now because x is default set to 8, so my adder has 8-bit wide ports by default. And this module is initially configured for 8-bit addition operation. Now interesting thing is if I need a 16-bit adder, then I will just change the value of x to 16. So this module is now flexible to handle the addition operation on the vector signals of different bit sizes. Let's quickly see how we will write our VHDL code for this. Entity half header is generic x colon integer colon equals to 8 bracket closed semicolon, port a in std logic vector x-1 down to 0, b in std logic vector x-1 down to 0, d out std logic vector x-1 down to 0 bracket closed semicolon and entity. If you notice that this is a minor change, we just updated the range from a hard-coded range which is 7 down to 0 to a flexible range which is x-1 down to 0. Now the range of std logic vector signal will depend on the value of a generic parameter x. If x is 8, then it will be 8-bit adder, and the range will be 7 down to 0. And if X is 16, then it will be 16-bit adder, and so on. So you can see that this module is now adaptable for the addition operation of the STD logic vector signals of any size. And this is one of the key benefits of using Chandix in your VHDL design. Now let's say we have an application where we wanted to use two 4-bit numbers and two 8-bit numbers. This is a good example to understand the use of Chandix. In general, you have to instantiate two separate adder components in your design to achieve this requirement, right? One component will be configured as 4-bit adder and the another one for the 8-bit adder. So this is our top module. And both of the addition components are instantiated inside this module. Okay. So we instantiated two adder components within this top level module. One for the 4-bit addition operation and another is for the 8-bit addition operation. Now let's see how you code this top level module using Chandix without changing anything in the adder module. This process is straightforward. For the first addition operation of 4-bit signals, we map the generic value to the 4. And for the second addition operation of 8-bit signal, we map the generic value to 8. Note that we have just mapped this generic value in the top level module. Our adder module is same. We are not changing anything on that module. So this is a conceptual view to showcase how these components will be instantiated and configured. Now let's see how we will implement this in the VHDL code. So we instantiated two components. First is the adder module for the 4-bit adder. We named this instance as adder 4-bit and we mapped the generic parameter n to 4 here. Means in the adder module, now the signal range will be 3 down to 0 for this instance and it will handle a 4-bit addition operation. Note that I have not written the port mapping here to make this look clear. But in your VHDL code, just write the port mapping after mapping the generic parameter. It is just like we did earlier in the component instantiation section. Next, let's instantiate the 8-bit adder. So this is named as adder 8-bit. Notice that we always try to write the relevant naming conventions so that we can clearly identify the purpose and configuration at the time of reviewing. So remember this as a good coding practice always. Now coming back, so to configure this 8-bit adder, we simply map the generic parameter n to 8. Now this will handle a 8-bit addition operation. So it's that simple. Okay, let's have a quick brief. Generic in VHDL function as a special type of constant that provides a powerful tool for parameterized designing. By using generic in VHDL, you can configure each instance according to your specific need, and that too without altering the core designs. So your modules become more flexible and they can be used in the wide application. Like in our example, we created a flexible bit adder that can handle data of any bit sizes. So this is the power of Chandix in VHDL. So try it and create more adaptable and reusable components for your design. Okay, so that's it for today. I hope you had a good overview of Chandix in VHDL and parameterized components in VHDL. In the next session, we will be talking about conversions in VHDL. So stay tuned for the update. If you did not subscribe till now, then please do subscribe to learn and grow community for regular updates. If this video is informative, then please like this video, comment on video, and don't forget to share. Thank you for watching.